So the compactness theorem also tells us a lot about cardinalities of models. So let's look at theorem 5.7 on page 83 here. So that says if a theory, so a set of sentences in a language has got arbitrarily large finite models, it must have an infinite model. So again, a theory just means a set of sentences. So arbitrarily large finite models then gamma has an infinite model. So just notice what the moral of the theorem is. The moral says that finiteness, just being finite, can't be characterized by a set of sentences. I mean, there may be particular theories that do restrict their models. For example, you can write down a theory that says that there are only 5 objects. But then that won't have arbitrarily large finite models. It only has models of size 5. So there are theories that will enforce that the interpretation is finite, but it can't be that there is a theory that has arbitrarily large finite models and no infinite model. So finiteness alone cannot be characterized. By as a set of axioms. And how does the proof go? Just as there in the notes. So just find a sentence sigma n so that if M is a structure in which sigma n is true, this can only happen if the size of the domain of M is at least n. So such a sentence just says there exists V0, exists V1 up to a Vn, and they're all different. We've seen such sentences before. So there are, well, at least n, not exactly, at least n things. So let delta just be the collection of these sentences, together with the theory gamma that we're thinking about. So we're going to use compactness again. So every finite subset delta 0 contained in delta has a model. So the proof from this claim here is, well, if this is finite, it can only contain finitely many of these sigma n's. So let m be larger than any n so that sigma n is in delta 0, right? As delta 0 is finite. And we've hypothesized that gamma's got arbitrarily large finite models. So all I have to do is find a model for gamma that's got m elements. So let m prime be any model of gamma with at least little m elements. So then m prime is a model of this delta zero here. So this finishes the claim. And now I say by the compactness theorem, delta has a model. So there is some m tilde, which is a model of all of delta. But because delta contains all of the sigma n's, doesn't have any finite size. It must be infinite. So the cardinality of the domain of m tilde, call it this, is not finite. So we're finished there on this one. So definition 5.8 says property P of models or structures is finitely axiomatizable if there's a finite set. Finite set of sentences in the language and let's call the finite set sigma, so that if I take any structure, if it's a model of this sigma, if and only if M has got property P. So it's a way of saying, right, we just have to check these finitely many things in this structure, and then we'll know that it has property P here. So this is rather like the idea of a theory being finitely axiomatizable. We said a theory was finitely axiomatizable if I could find a finite set of sentences so that the two sets have the same consequences. So here we're saying I've got a property of models. It's finitely axiomatizable if I can find a finite set of sentences which guarantees that M has the property here. So this is similar to finite axiomatizability of theories. We said a theory T is finitely axiomatizable if there's a finite T0. It doesn't have to be a subset of T, but it often is. Such that for any for any sentence phi, T0 proves phi if and only if T proves phi. But notice then that the models of T0 are precisely the models of T. Right? Because everything that's true in a model of T here, such phi's, for example, we can prove from T, right? These are all going to be true in models of T0 here. So if T is finitely axiomatizable, the property of being a model of T is given by a finite set of axioms. So if T is finitely axiomatizable as a theory here in this sense, then the property of being a model of T, so this would be the P property capital P in the previous definition, is finitely axiomatizable in the sense of that definition. In the sense of definition 5.8. That's the finite set of axioms that'll do the job. Right? So the property of being a group, for example, is finitely axiomatizable. There are only 3 axioms. The property of being a strict partial order is also finitely axiomatizable. If you look back and see where that was defined, you'll see it's expressed by a finite number of axioms. So this is example 5.9. The property of being a strict total order is finitely axiomatizable. So this is the, see example 3.7, and then we add to that the statement that everything is comparable. 3.7 just gave us a strict partial order. So if R, we're thinking of R as a 2-place order relation, we just add on the single extra axiom that says everything is equal or one is less than the other. So it then becomes a strict total order. Lemma 5.11, you already saw as part of one of the homework sheets. The property of being a well-ordered set is not characterizable by any set of sentences. Right? By any set of sentences, whether finite or not. So this is not axiomatizable at all. Just like finiteness was not axiomatizable at all here. So here this was, I believe this was question 4 of problem sheet 4. So you can review that solution there. So continuing, lemma 5.12, let's see this, let's have that as optional. It's a voluntary lemma, so this can be omitted. Then let's move to example 513. So let mu n in the language of groups so mu n of v0 says that v0 has order less than or equal to n. Well, let's say it has exactly n here. So this is saying v0, 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 n times here gets you back to the identity element. Right? So groups where there is every element, where no element has a finite order, are called torsion-free groups. So we'd like to consider axiomatizing group theory for torsion-free groups. So let T be the theory of the three group axioms. And then plus an infinite set that says basically so each sentence here, this says that in EV0 here, its order is bigger than n. So I've got this collection of infinitely many sentences right here. So models of this theory are torsion-free groups. They're groups, and no element has a finite order here. But this is also not finitely axiomatizable. There's no finite set of axioms that'll do the job. We have to have this infinite set here. So let's see why. Note, any torsion-free group has to be infinite. It's just an observation. Because if it's got one element besides the identity, the square, the cube, and the nth power, these are all different elements inside the group here. So suppose for a contradiction, I've got a finite set of axioms. We have T0 finite, and T0 proves what T proves. So in particular, T0 proves all the axioms of T in this set, but there's only finitely many of them. So this is for a contradiction. So having the same consequences means, in fact, they must have the same models. So this happens if and only if T0 and T have the same models. Okay, but our claim is so if phi is a sentence in the language of group theory, And let's suppose this holds. Every model of T, so every torsion-free group, is a model of phi. So if then there's a natural number so that phi is true in any group G whose elements all have order greater than or equal to n. Now, the idea is if the claim is true, then T0 cannot axiomatize T. T0 cannot axiomatize T. And we see why. So for convenience, let's replace T just by the conjunction of the finitely many things in T and call it 0. So let gamma be the conjunction of the sentences of T0. Then gamma is a consequence of the axioms of T0. It's just their conjunction. So it's a consequence of T, because T, T0 have the same consequences. Because we're supposing for a contradiction, T and T0 have the same contradiction. So, again, by soundness, any torsion-free group is a model of gamma. Since they have the same consequences there. So if we suppose the claim true here, so by the claim here, for some n, gamma is true in any group G, all of whose elements have order greater than or equal to n. And now the point is that there are such groups which are finite. But ZP is a finite group where P is a prime greater than or equal to n. And here, all the elements have got order P. But T0 and T have the same models. So this is a contradiction because T only has infinite models here. This ensures T only has infinite models. So they have exactly the same models. and all those of T are infinite. And that's a contradiction because we've just found a finite model, ZP, for gamma, the axioms of T0. And all those of T are infinite. So this is our contradiction. So that would justify the example here, except we have yet to prove the claim here. So suppose any model of T is a model of phi here. So we suppose the antecedent, and for a contradiction, we'll suppose this consequence is false. So there's no such n, right? So for arbitrarily large k, say, right, we're going to find that for arbitrarily large k, there's going to be a group G, which every element is order at least k, but in which phi is false. So it's the negation of this here. Right? So there's no n such that for all groups of size or where the orders of the elements are greater than equal to n, phi is true, right? In every such group. So we'll find arbitrarily large k, in which phi is false in a group satisfying this property. Suppose the conclusion false of the claim. So we're going to use the compactness theorem. So let S be any subset of T together with not phi. Now, remember what T has. It's got the three group axioms plus a collection of these statements in. So S will only have finitely many of these. It's a finite subset of T. Right? So it's only going to have finitely many of these. So the K that we're going to be after is a K bigger than any of the n's mentioned in S. So let K be greater than any n for a mu n here mentioned in S. Here. Now, the supposition that we're taking over here, this conclusion, so let's call this let. So we suppose the conclusion here. So by supposition, right, there are arbitrarily large k in n for which there is a group. So two k's in here, let's call this L, for which there is a group G in which every element has order at least L, in which phi is false. So take a group G for an L that's bigger than K. So now what we have is, it's a group, so the group axioms are true here. Not phi is true in here, in case S contains not phi. And the K and therefore the L are big enough that they're beyond the statements saying that these things have small order. So S is true in G. But S is a finite, arbitrary finite subset of T. So I appeal to the compactness theorem. T has a model. Sorry, T union not phi. We're looking at finite subsets here. T union not phi has a model. But that's a contradiction, because we're assuming every model of T is a model of phi here. So this finishes the example here at this point.